Hi everyone, I'm Suresh. I'm a first-year PhD student at the Robot Perception Lab in the Carnegie Mellon University Robotics Institute. And this is our virtual presentation on active SLAM in underwater environments for sonar. The motivation for this work is that teleoperation underwater is hard, especially in cluttered environments such as that pictured here. This is true even if you do have a map known a priori. And most inspection tasks necessitate some sort of volumetric coverage, which is ideal for a planning approach. Whereas noisy odometry and sensing information motivate SLAM for long-term operation. And drifting knowledge of this free space, like that pictured on the bottom right, leads to potentially dangerous trajectories that a vehicle might take. This middle ground between SLAM and planning is ideal and is formally known as active SLAM. This robust autonomy enables inspections of areas of interest such as ship hulls, bridges, dams, reactor pressure vessels, and ballast tanks with minimum human intervention. Um, Formally, our work is an active SLAM solution for exploration of unknown underwater environments using multi-beam sonar. And our contributions are a global saliency metric for submaps that use real-world sonar data and build a visual dictionary, a revisit policy based on vehicle pose uncertainty and information gained from the sensor, and an evaluation of experiments in both simulation and real world. In related work from the planning side, a next best view planner addresses the problem of volumetric exploration by using a sampling-based planner and exploring directions of best volumetric coverage in an occupancy framework such as Octomap. And it executes the first stage of this branch and repeats the process for good coverage. From the side of SLAM, underwater sonar SLAM is usually done via submaps, which optimize the pose graph using ICP alignment of sonar scans to give you good maps such as that on the right. For completeness, a sonar submap is created by accruing scan information from vehicle odometry. And with this motion that creates a sweep, you can get local submaps that coalesce to give you a global picture of the entire environment. Putting both these ideas together, we have previous work on virtual occupancy grid mapping, which takes a postgraph SLAM framework and combines it with volumetric planning to give you an occupancy representation that is a sum of these local submaps and is deformable with time. The problem is this is not an active method, which is something we intend to fix. Planning and SLAM do not talk to each other, and if a trajectory gives no good loop closures, the uncertainty of the vehicle grows unbounded with time. So this brings us to the idea of active SLAM, and it is to generate navigation trajectories that complement both mapping and localization. If SLAM and mapping are considered mutually agnostic, these errors will affect each other. So we would want to phrase it as a problem that given a robot with high pose uncertainty, we'd want to revisit places answering these three questions of where, when, and how. Where would be good places to revisit? When would we want to trigger these revisits based on explore-exploit trade-offs? And how would we want to get back to these places, especially given we have a directional sensor? And we find that SLAM performance is correlated to navigation strategy. To ground the talk, we first give context of what the vehicle and the sensing payload we have is. We use the Bluefin Hovering Autonomous Underwater Vehicle, or HAUV, in both our simulation model and our real-world platform experiments. Our vehicle pose is 6 degrees of freedom with 3 different degrees of freedom on the plane and direct measurements on the rest of the degrees. It's equipped with a Ditson profiling sonar, which has 96 beams at 29-degree horizontal field of view and a 1-degree vertical field of view. Our approach uses a factor graph, which is a bipartite graph that comprises of variables to be optimized for, and some factors that constrain the entire system. And if we assume that the likelihood is proportional to a Gaussian distribution, and with some algebraic manipulation, we get a nonlinear least squares system. And this can be solved using either standard methods, or in this case, we opt for an efficient incremental inference method that uses smoothing and mapping, which is called ISAM. Our pose graph is similar to that of the virtual occupancy grid map framework, where we have ICP factors that constrain the vehicle poses in the pose graph. And these local submaps that you can see on the top are adjusted by rigid body transformations anchored to these base poses. All this works well in a passive SLAM framework, but given the active problem, we'd want to find out first, where do we go to bound our pose uncertainty? There's been a good deal of work in the visual analog of this problem, where Kim and others use a bag of words in an underwater visual environment. to give good places to revisit in a pre-planned trajectory. So the inspiration is, can we port this to a submap-based domain and instead for a sampling-based exploration framework? So we first start out by collecting real-world sonar sensor data and building a vocabulary of the environment. We have a pipeline that computes the key points and takes sharp descriptors, clusters them into visual words, and gets a scene dictionary out of them. We then draw from statistics, where we measure the inter-submap uniqueness of all the points. And here we compute what we call as inverse document frequency, which we normalize to a ratio of 0 to 1, where 0 means lower scores, which are often seen in their environment, and higher, rare, and good. As a sanity check, we first look at the top and bottom measurements that we have, and we see that high scores pertain to edges and complex objects in the environment, which are easily discernible, and low scores are repetitive patterns and structures. So we have good places to revisit. How would we get back to these? Retrace a cached RRT that we have, which got us to the place in the first place. And this is similar to a network of reusable paths, which is worked by Stelling and others. Finally, when do we decide to trigger these revisits, or what is our utility function? So we have a policy that does virtual occupancy grid map exploration or next best view if the uncertainty is below a threshold, or otherwise we would trigger a revisit policy. So here we're focused on the revisit policy. So the uncertainty threshold we use is similar to that in other active SLAM literatures, which is the optimality criteria. It is the Lth root of the covariance determinant, which is proportional to the uncertainty of the ellipse of the state parameters. And here we consider only 3 drifting degrees, so we take the third root of that. And we get a ratio UR, which is the uncertainty ratio, which is the maximum allowable vehicle uncertainty. So you can visualize this here, where we propagate this uncertainty over the direction of the revisit of a path with growing ellipses. And this forms the first point of our penalty function that we have. The second part of our penalty function, it comes from gain best, which is a summation of the unmapped voxels that we encounter over the path. And together we try to minimize this penalty function. So now we have all 3 pieces of the puzzle for our active SLAM method. To put this into context, our work fits into computing the glossy framework and then using it for revisit and executions. We use an experimental simulation environment, which is in Gazebo with our HAUV model. The environment is the metric model of the real-world tank experiment with some more interesting objects in it. We have an initial free space assumption and unknown occupied and free voxels that get fleshed out with time. We also have an RRT tree that we see with new nodes and previously occupied ones. And we see that we explore the free space over time and get a better sense of the environment. Once we drift beyond the threshold, we have a salient revisit path, as you can see, which was facing the piling straight up. We benchmark this with respect to policies that have either random revisits or no revisits at all. And we see that there are a greater number of loop closures over time, which surpasses the baselines, while we also do not compromise on the volumetric exploration or the number of voxels you explore. At the same time, we also compute the uncertainty ratio versus the number of submaps. Here, loop closures are shown with the cyan circles, and the revisits are in yellow. And we see that the mean uncertainty is closer to the threshold, and without revisits, this skyrockets and exceeds that. Finally, we have some quantitative metrics that show that the active method has a least cloud-to-cloud error and has a greater number of loop closures. In a real-world experiment in an underwater tank, we image a piling-like structure here, as you can see. And we also build a map on the fly and execute our active revisits. Here we can visualize the ground truth point cloud versus our resultant map with a heat map showing cloud-to-cloud error. We visualize a cross-section of the final occupancy map and some examples of good and bad loop closures. And for future work, we'd like to use methods like segmap to enhance our map representation, integrate visual methods for sensor redundancy, and explore opportunistic methods. Thank you very much for your time. I'd like to thank my co-authors. You can check out my publication here and contact me